Hello, my name is Han Tran, and in this video we're going to be taking a look at an example dynamics problem. In this problem, we are given that there are three tanks that are connected in series. In a previous video, we looked at all the information that we were given and wrote out equations for the flow between the tanks, as well as the differential equations that can be used to solve for the fluid heights in the tanks. In this video, we're going to be reviewing that information, building on those concepts, and using everything to write a script in Python that will allow us to create a simulation for what the fluid heights in the tanks will behave like. To begin, we're just going to do a quick review of information that we covered in the previous video. If you're looking for a more detailed explanation, go ahead and go look at that video. But we're just going to review all the information so that we have it all together before we start writing out the code. And so here at the top, what we did was we drew a diagram of the problem that we were given with the three tanks, as well as labeled their cross-sectional areas, their initial heights, and the proportionality constants. We also labeled the set point that we want. And then we moved on to write out the equations for the flows between the tanks. And so we wrote the equation for the flow from tank 1 to tank 2, from tank 2 to tank 3, and then out of tank 3, so this flow, and then this flow, and then this flow. And then we used that information to write out equations for the change in volume. But first we talked about how the change in volume is due to the change in fluid height, since the cross-sectional area is remaining constant. If it were like a cone or something irregular shaped, the cross-sectional area would not remain constant, but since here it is a tank that has a constant cross-sectional area, we can take that out of the differential equations and just use the change in height as a part of the differential equation over a change in time. And so we also talked about how the change in height is due to the flow in minus the flow out, is that's going to result in the change in height. And so we wrote out the equations for the volume in tank 1, in tank 2, and tank 3. And then what we did was we isolated the differential equations for the different fluid heights by dividing by the different cross-sectional areas. So that gave us the differential equation for the fluid height in tank 1, and then the differential equation for the fluid height in tank 2, and then the differential equation for the fluid height in tank 3. And then we also talked a little bit about the set point. So we knew that the set point was at 4 meters. And we also talked about how if the set point is greater than the actual height, then the amount of fluid added in needed to be increased, or the amount of fluid in the tank needed to increase by adding in more fluid. And then we talked about if the set point is less than the actual height, we needed to decrease the amount of fluid in the tank. And so we wrote out the equation over here that the flow in is going to be dependent on whether it is below or above the set point desired. And so that's going to be the difference between the set point and the actual height multiplied by a proportionality constant that is established based on temperature and materials of the tank, of the fluid, and just other factors that go into how fast the fluid is moving. But so what we essentially did was we defined a equation for a proportional control. So a proportional control is a very simplistic control that is used sometimes in systems. Rarely is it used for more complex systems because it's not always the most accurate, and there is a decent amount of error that can be accounted for. But in this problem, the proportional control is the one that we are given, as it is the most simple. And so what a proportional control does is it looks at the proportion between the set point and the actual height, or so the desired height and the actual height, or the set point and the actual fluid height. And it looks at which one is greater, which one is less. It looks at the proportion, and based on that, it determines whether the flow in needs to be greater or less. And that is exactly the equation that we wrote here. So the flow in is equal to the proportionality constant minus the difference of the set point in tank 3 minus the actual fluid height in tank 3. And so having everything established here, let's go ahead and move on over to Python and code out a simulation that we can use. And so the first thing that we want to do is we want to import functions that we are going to be using in order to write this simulation. So we're going to be using NumPy. This is a function pack that will allow us to perform mathematical equations and so much more, but we will mainly be using it because we have absolute values here. And We also are going to be using something called solve IVP. Solve IVP is something that can be used to solve for unknowns of ordinary differential equations, and that's going to be from the function pack scipy.integrate, and we are going to import solve_IVP. Once we actually get to the solve IVP function, we'll talk a little bit more about what all solve IVP includes and what it can do for us. And then in order to see our simulation, we are going to be creating a plot. So we are going to import plotly from plotly.subplots. We are actually going to import make_subplots. This is going to allow us to make the plot. And now that we have all the functions we're going to be using, we are going to move on into putting in all of the information that we are given in the problem. And so all of that information is going to be the proportionality constants, the cross-sectional areas, the initial heights in the tanks. And so let's just go ahead and put that information in. So we are given the cross-sectional areas of tank 1, tank 2, and tank 3. So the cross-sectional area of tank 1 is 0.5. The cross-sectional area of tank 2 is 1, and the cross-sectional area of tank 3 is 2. And that is going to be meters per meter squared. So what we're doing is we are, again, defining our givens. We are also given the initial height of tank 1, tank 2, and tank 3. So the initial height of tank 1 is 0.5 meters, the initial height of tank 2 is 1, and the initial height of tank 3 is 2, and these are all in meters. We are also given proportionality constants of the flow from tank 1 to tank 2, from tank 2 to tank 3, and out of tank 3. So from tank 1 to tank 2, it is 0.1. From tank 2 to tank 3, it is 0.1. And out of tank 3, it is 0.1. We are also given the proportionality constant for the flow in, right here. And that is Kc. So we are going to shift enter. Now up here, what we're going to do is for solve IVP, here we will write it down here. So for solve IVP, we need a function and an independent variable, and the right sides of the differential equations. And so since we need that, what we are going to do is we're going to go up here and we're going to define a function. We'll just call it simulation since it's going to be used for that. And in this function, we need an independent variable and the unknowns. So it's actually going to solve for unknowns. So while we define the function, we need to give it an independent variable and an unknown. So we will be having the independent variable be time, since it's change in fluid height over a change in time. So we're just going to have the change in time be independent. And so that's going to be, we'll call it t. And then we need an unknown, and we'll just call it v. So the unknown that we are solving for is actually the different fluid heights. So the fluid height in tank 1, the fluid height in tank 2, and the fluid height in tank 3. That's what the unknown b is going to give us. And so what we did there is we just split up the information that's going to be returned to us in b. And so we're going to want the right-hand sides of the equation returned. So if we go over here, we look at the differential equations that we established. We're going to want the number from this, number from this, and the number from this, the number from the right-hand sides of the equations. So we are going to input that as our return because that's the information that we want from the function that we are defining. So we want it returned as an array. And so the first one is negative flow from tank 1 to tank 2 over cross-sectional area of tank 1. And then the second equation is the flow in plus the flow from tank 1 to tank 2 minus the flow from tank 2 to tank 3, all divided by the cross-sectional area of tank 2. And then the third equation is the flow from tank 2 to tank 3 minus the flow out of tank 3, all divided by the cross-sectional area of tank 3. And so now that we have the right-hand sides of the equation all put in, there's a lot of information that Python is saying it doesn't have from us. For example, it doesn't have the equation for flow from tank 1 to tank 2. So let's go ahead and define that. When we were writing our equations, we said that the flow from tank 1 to tank 2 is the sine of the difference in the fluid heights of tank 1 and tank 2 multiplied by the proportionality constant of tank 1 to tank 2 multiplied by the absolute value of the difference of the fluid heights of tank 1 minus tank 2 to the 1/2. So we're going to use numpy dot sine of the fluid height in tank 1 minus the fluid height in tank 2 multiplied by the proportionality constant of tank 1 to tank 2. So let's change this so it's a little more clear. Multiplied by the absolute value of the difference between the fluid height in tank 1 and tank 2 to the 1/2. And that's going to be the flow from tank 1 to tank 2. And if we look at the flow from tank 2 to tank 3, it's also the sine of the difference between the heights in the two tanks multiplied by the proportionality constant from tank 2 to tank 3 multiplied by the square root of the absolute value of the difference between the heights of the fluid in tank 2 and tank 3. So we're going to go ahead and put that equation into our code. So we're going to use np.sine of the difference of the fluid height in tank 2 and tank 3 multiplied by the proportionality constant between tank 2 to tank 3 multiplied by the absolute value of the difference between the heights in tank 2 and tank 3 to the power of the 1/2. And then we also is telling us need to define the flow out of tank 3. So if we look in our notes here, we wrote in the previous video that it is the proportionality constant out of 3 multiplied by the height of the fluid in tank 3 to the 1/2. And so now that we have the flow between the tanks established, we also need to define the flow into tank 2. And we wrote that in the previous video to be the proportionality constant multiplied by the difference of the set point minus the actual fluid height in tank 3. And it is telling us that we have not defined the set point that we want for tank 3. So the set point that we want for tank 3 is 4 meters. So we're going to shift enter and shift enter. And so now that we have our function and our givens defined, we can move on and finally use this solve IVP to solve for the values of the fluid heights. And so solve IP, what it needs from us is it needs a function, which we defined as simulations. It needs an independent variable, which in this situation, we are going to be using time. It needs the initial values, so the initial fluid height. And then it also needs a method for which it needs to be solved. So we're going to be using Redo. It's a method that solves for ordinary differential equations. And then we are also going to be needing to tell it that the dense output is true. If we don't tell it it's true, it is assumed to be false. But in this case, it is true since we are solving for continuous solutions. And so having all of that stated up here, let's just go ahead and put that in as code. So we're going to use solve underscore IVP. And so we need the function simulations, or simulation is what we named it. We also need independent variable time. So we actually have not defined independent variable time yet. We need to define how long we want the simulation to run. So the time at the end, let's just say we want it to be run for 100 seconds. Now we have the time defined. So it's going to run from 0 seconds to the end time. And then we need to input the initial values, or the initial heights, which we have already defined up here. So we're just going to copy and paste it in to make sure we do it correctly. So that's going to be the initial values. We need to provide a method. The method is going to be Redo. And then we need to tell Python that it is going to be true for the dense output. So we're going to shift enter, and we are given all of these values. We're given the array for the time, and we can see that the solve IVP ran as a success. And so we only really need the sol here. What that's going to do is it's going to allow us to later on use it to plot. And so we're going to have to give this a name. We can name it the tank's FH for the tank's fluid height. We're going to shift enter. And so now, if we were to put in tank's FH, that's not going to give us the values of the fluid heights. But what it can do is allow us to use that information to create a plot that would show us the simulation. So what we're going to do is we are going to first define our x-axes and our y-axes, or the x values and the y values. So the x values are going to be the time, and so we can call that plot t-plot. And so these are the times that we're going to be used to plot on the simulation. And so we're going to use np.linspace. So what this is going to do is it's going to create a bunch of values from a start value that we give to an end value that we give, all linearly spaced. And so the start value, we want it to start at 0 seconds. and we want it to run for a specified amount of time, which we defined up here as t end. And let's just say we want 500 values in between. We also need to define what the y values are going to be. So the y values are going to be the heights of the fluid in the tanks. So that's going to be the height in tank 1, the height in tank 2, and the height in tank 3. And what these heights actually are they are the tanks FH. This variable here that we defined earlier is the solve IVP. So if we were to put in tanks FH, which is what we named it, but it's really just a solve IVP function, and we were to solve it at the times in the t-plot, what that's going to do is it's going to, this equation, or this function that we wrote here with all the function, the independent variables, the initial values, the method, and the dense output, it's going to take that and it's going to run it for the t-plot times that we defined up here. And so now we can make our simulation. So we are going to name it big, that's just what we're going to name our plot. We can name it anything. Actually, let's just name it simulation plot. And so we are going to make subplots, make underscore subplots. This is going to create the plots. And then what we need to do is we need to add to the plot. So we're going to add to the simulation plot. We are going to add underscore scatter. And so we're going to add the x values, which is t plots. And then we're going to add the y values. So we're going to do this for tank 1. So the y values are the fluid heights in tank 1. So y equals h1, which is fluid height in tank 1. The mode we're going to be using is we're going to be using lines. So it's going to create one continuous line. And we are going to name it fluid heights in tank 1. And then now we need to add a second line, and on the second line we need to add the tank 2 fluid heights. So we're going to do simulation plot dot underscore scatter. So the x values are going to be the t-plot values that we defined. The y values is going to be the fluid heights in tank 2. And then we're also going to have this be lines again, so it's going to be one continuous line. And we are going to name this fluid heights in tank 2. And then lastly, we need to add the fluid heights in tank 3. So we're going to do simulation plot dot add underscore scatter. The x value, that's going to be the time values again, so t-plot. The y values are going to be the fluid height in tank 3, so that's going to be h3. The mode, we are going to do lines again so that we can see the lines of the fluid height. And we are going to name this line fluid height in tank 3. And then we're going to shift enter. Did I miss something? Lines. There we go. Now we're going to shift enter. And this is our simulation plot. So this shows, if we look at the fluid height in tank 1, what it's going to happen is it's staying constant. In tank 2, it is going up. And in tank 3, it is going down. And so now if we were to change around the values to maybe be 500 seconds, we can run the simulation again and see the way that the fluid height changes, although the fluid height of tank 1 is not supposed to remain constant. So if we were to go back here and see what should be changed because that is not correct. Let's shift enter all the way through. So if we were to go back and check our equations, so here, when I wrote out the equation for flow from tank 1 to tank 2, instead of having the difference between tank 1 and tank 2, I had the difference between tank 1 and tank 1, which would be 0. And so that is why it was constant. So sometimes we make typos, sometimes we have fat thumbs and put in the wrong numbers, but we went back and we checked. So now we're going to shift enter, go all the way through. That looks a little better. It is not constant anymore. So as we can see, the fluid height in tank 1 and tank 2 start down at their initial values, and then they tend to shoot up until they reach a steady state. And then for tank 3, what happens is it starts at its fluid height and it decreases, and then it increases and gets to its fluid height at around 2. And so what this shows us is it's not reaching the set point like we want it to. So we can play around with it. We are given in the problem the proportionality constants, but if we were to change it, let's just say we change the proportionality constant to 1, it's going to have a complete different effect. So the fluid height now is at around 3.6, which is a little closer to 4, but it kind of overshoots the, like it decreases and then increases sharply and then reaches its steady state. Same with these values, they increase and then reach its steady state. We can change it to 0.5 and see how that affects it. So this actually causes it to have a dip in tank 1 and then a sharp increase in tank 2, and then tank 3 pretty much just gradually increases till it reaches its steady state. We can jack up the proportionality constant in hopes that it will reach closer to the steady state. And it actually creates all these kind of waves of increasing and decreasing in tanks 1 and 2. And if we look, there's actually the same kind of waves in tank 3. It's just a little smaller, and it will reach its steady state at around 3.9, which is the closest we've gotten to the initial or the set point that we would like. The only thing is, do we want tanks 1 and tanks 2 to increase and decrease and reach all the way up to 89 meters? Not necessarily. So what the simulation allows us to do is it allows us to put in proportionality constants. It allows us to see how we can change the proportional control in a way that will allow us to get the dynamics of this system to work the way that we want it to. So proportional controls, like I mentioned earlier, are not super accurate. They tend to have a lot of error and struggle to reach the set point that is intended for them. And so a lot of times it's difficult to achieve what the goal is with just a proportional control. There's plenty of other controls out there that are more complex, more accurate. This is just the one that we used in this problem, but we are able to code out a simulation and see how we can change the proportional constant or the proportionality constant in order to change how it affects the amount of fluid in each tank. And we can play around with it, not only mess around with the proportionality constant, but we can change the time. Let's say we run it for only 10 seconds. That's going to shorten our graph significantly, shorten our simulation, and we can see that it reaches nowhere near the set point that we desire. We can increase the time, so we can go to, let's say, 10,000. That's going to take a little more time because obviously it's running it for more values. But yeah, so we are able to create a simulation based on the amount of time we want it to run, based on the proportionality constants, based on the initial fluid heights, and as well as the control that we're using. So we wrote a control or a script for a proportional control, but you can write it for other controls. And having this simulation allows us to change around values and not have to actually change around the real situation, and that can save us time. It can save us materials, it can save us cost, and it can be way more efficient in the long run, except finally. So as I say, maybe it's not as efficient because that was taking quite a while to run, but finally we got it to run. So we can see that it reaches it only reaches 1.9. So increasing the time doesn't really necessarily have that much of an effect, because once it reaches its steady state, it's at its steady state. So we're going to go this back down to just 500, and so we can show the final simulation for a 3-tank system that has the initial heights that we were given, the cross-sectional areas that we were given, and the proportionality constants that we were given. This is the final simulation that we got by writing a code in Python.